So this is the second in a series of circular motion sample problems. The last one we did was the conic pendulum. And I hope that you notice that this one will become very similar to the conic pendulum one. It is what we would call a banked curve. So you'll notice that the car is on a curve, on a road that is curved this way. You might think of the Indianapolis 500, how whenever it comes around the corner, they have it curved. Maybe when you're getting onto an on or off ramp of the interstate, you'll notice that the angle of that is curved inward towards the center of that circle. And that's all to allow you so that you don't need as much friction to go around the corner, because some of that is getting pushed into the ground instead of sliding you off of the curve. So because all the accidents on a specific curved roadway in town, the town wishes to bank the curve so that a car won't have to rely on friction in order to make it around the curve without skidding. The speed limit for this road is 45 meters per second. So that's the maximum speed that you can go on the road. And then the average mass of the cars rounding this corner is 1,300 kilograms. By the way, that's kind of a large average mass, but that's okay. So first off, draw a force diagram. If I picture my inclined plane here, and here's my car, and picture the car is coming out of the screen towards me, then I'm still going to have a normal force, that's the hill pushing outward perpendicular, and I'm going to have a force of gravity that is the pull down of the hill that way. Now, in the past, remember that we used to adjust this into a parallel and perpendicular frame of reference whenever we talk about inclined planes, because the car was sliding down the hill. But remember now that the car is actually coming out of the screen towards us. And where is the center of the circle? Well, the center of the circle is this way. So it makes more sense for us to go back to the X and Y axis to frame of reference. Now, on the AP test, then this would be our complete force diagram. We wouldn't add or take anything away from that. However, in order for us to do this problem a little bit more easily, we might add our own force diagram that says, okay, here's the force of gravity, here is the normal force coming out, and if I'm going to go on an XY axis, then wouldn't it make sense for me to break up the normal force into a normal part that is in the Y direction and a normal part that is in the X direction? And the answer to that is yes. So if you think through it, we have our angle of the hill here, which is going to be that. As that angle gets smaller, which one of these two angles is going to get smaller? It's got to be this one here. So that's also got to be the angle of the hill. Once I have these components here, I can ignore this guy, and so I'm going to erase it to make it go away. And again, notice how similar this force diagram is to that of the conic pendulum. Can't we say that the normal force in the Y direction is equal to the weight, because the car isn't going up or down that way at all? And then also, can't we say that the normal force in the X direction is equal to the centripetal force, or the force that is pulling the object towards the center of the circle, that mv squared over r? And the answer to that is yes also. So if I take these, then I'm going to just move them over here a little bit so I have space on the other side. Okay, so here we go then. At what angle must the road be banked for the car to travel at this 45 meters per second if the curve has a radius of 21 meters? Now, in order to keep this going 45 meters per second with a car at 1,300 kilograms, I'm going to imagine this angle is going to have to be a really, really big angle, kind of like you see in the picture here. But we'll see where this goes. So when we do that, if we're looking for the angle, there are a couple different ways we could do it. We could take these two equations down here and simultaneously solve them, or we can look at them and say, which is the same thing, what relates our fnx and our fny? Well, for that, I would say, doesn't the tangent relate that? So I could say the tangent of theta, and if I'm doing the tangent of theta, then won't my opposite be the x value? So I'm going to say fnx over my adjacent fny. And then can't I plug those guys in? So up here I could say mv squared over g, and down here I could say mass times, not over g, over r. And down here I could say mass times gravity. And again, does it matter what the mass of the car is? Actually, it doesn't. It could be a tricycle traveling at 45 meters per second around that curve, and it will still have the same theta value. So if I simplify that, I'm going to get the tangent of theta equals we just canceled those out, equals v squared over rg. And then we can plug in values. 45 squared over a radius of 21 times 9.8, and that gives us a tangent of theta. And then when we inverse tangent that value, that's going to give us a theta value of 84.2. And so my hunch was correct that that is going to be a really big angle for the car to travel around. Now, just to go back to talk what I was saying earlier, in order to solve these, I could look at this and say, well, Fn times since this is the y, it's adjacent, it's going to be the cosine of theta is equal to mg. And over here, I'm going to say that Fn times the sine of theta is equal to mv squared over r. And if I solve this guy for Fn, Fn is equal to mg over the cosine of theta. And then I plug that in over here. I'm going to have mg over the cosine of theta times the sine of theta equals mv squared over r. And guess what? We end up with the same thing. Won't both of our masses cancel out? And then doesn't this sine divided by cosine become the tangent of theta, v squared over r? And if I divide my g over, then I end up with the exact same equation that I had up there. So kind of cool the way the math works and the physics works for that. Lastly, what is the normal force that the road puts on the car? We're going to have to break it down into partly one of these. So now that we have what that angle is, I look at these two equations, say, well, probably the easier one for me to do would be this one. So I'm going to say the normal force times the cosine of theta is equal to mg. That normal force equals mg divided by the cosine of theta. So I can put my mass in 1300, put in my gravity 9.8, and divide that by the cosine of the angle we just found, 84.2. And when we do that, we end up with a normal force of 1,26068 newtons. And that's how much force the road puts back on the car. So again, a banked curve, notice that it's very, very similar to the conic pendulum. So we have the force that's pulling it towards the center of the circle. We have the force that is canceling out in the up and down direction. And then playing around with the mv squared over r's in order to solve for either the angle or the tension or anything else that you would need, the normal force that comes out of that problem.